Use an electric field called as electrostatic field. That is called as electrostatic, where magnetostatic is nothing but electric charge in motion, that is current produce magnetic field. Okay, so in a conductor, both electric and magnetic field will be there. But at static, at static condition, we are studying these concepts. Let me move toward what is the today's class content, that is called as magnetic flux density. So in last class itself, I have given some comparisons on two parameter. One is the dielectric flux density and the magnetic flux density. So what is the denotation has been given, that has been explained in last class, and also some matrices and some other postulate may be differ in the case of magnetic field. So almost the same resemblance property will be there, but some reverse property also there. So those things only, reverse property or negative property, that only we should notice. So that one only mostly they will twist in your recruitment exams also. Okay, so while you preparing itself, in that manner you have to prepare. Okay, in that manner you have to prepare. So this is one we have seen in the last class, like magnetic flux density, electric flux density. For magnetic flux density is denoted by B. For electric flux density denoted by D. Okay, a minute. Okay. So in previous classes, these contents we have studied. Okay, so that is magnetic flux density, electric flux density. For magnetic flux density, uh, students, if anyone waiting outside, please let me know, so that I will give admit options. And if anyone having any doubts or clarification, you can interrupt me and you can ask. Okay, so don't wait at last. Also, you can interrupt and you can ask me a doubt. And if it is not clear to your end, also you can ask me. Okay. Okay. The magnetic flux density is nothing but the magnetic flux passing per unit area. So it is denoted by phi by A. Okay. Phi is a flux and the denominator factor is a area. Okay. So we already know that B is equal to mu into H. So the H can be rewritten like phi divided by mu into A. So this is one expression, and we have termed each and every symbols what it represents for. Okay, so mu is nothing but a permeability. So everyone will get confused with this factor. Okay, mu and epsilon. Epsilon is nothing but permittivity. Okay, permittivity, where permeability is nothing but something accepting or attracting. Okay, so where mu naught is nothing but the constant for the free space, it is pi into 10 to the power minus 7 Henry per meter, and mu r is nothing but a relative permeability. So like this in magnets or electric field also we have studied like epsilon, epsilon naught, epsilon naught. Okay, let me come to the next parameter called as the magnetic flux. So for magnetic flux, phi is equal to B dot A. Okay, B is equal to phi by A we have to know already. So then from that expression we can write phi is equal to B dot A. So then how can we define the magnetic flux. How can we define the magnetic flux? Let me define what is the magnetic flux through this expression itself. The magnetic flux is nothing but the total magnetic flux is passing through any closed surface is equal to zero. This is also one of the term or one of the condition for the magnetic flux, but the definition. Okay, but the definition can be given like this: the magnetic flux is defined as the flux phi passing through any area, passing through any area. Students, can you able to see my writing content in your screen? Is it clear?
Yes,
Can
sir.
you quickly respond? Yeah, thank you. So this is nothing but the definition for your magnetic flux. So it can be mathematically expressed like this. Flux is denoted by the symbol phi, which is equal to that is magnetic flux is passing through any area. That is a B into A we will tell. Okay, so in as per the previous slide, phi is equal to B into A. But please see, it is not a single flux. Okay, it is not a single flux. It will be generate to entire conducting element. So it is full density. So b dot that is the integral of b dot ds. So whenever we are relating with mathematics, okay, so one point form alone everything has been given. If it is integral means it is for one density or one volume. Okay, one volume. So the same expression can be given in terms of Gauss law also. So the Gauss law for electric field we already studied. So once again I will recap what is meant by Gauss law for electric field. So sometime I am telling electric field, but I will write E field. Okay, so this is denotion. Near textbook also, if you see, for magnetic field H field they have given, for electric field E field has been given. Okay, so that one you have to remember. I will for your remembrance I will write it here in the first slide. So for magnetic field, okay, for magnetic field it is denoted by H field. For electric field is denoted by E field. Okay, so don't get confused even if it is denoted by H field or E field. Okay, so then what is the Gauss law for E field? The total flux is passing through any closed area is equal to the charge enclosed. Okay, so this is the one we already studied. Anyway, I will write the statement that the total flux passing through any closed surface is equal to the charge enclosed. Okay, so this is called as the Gauss law for the electric field. So then as per the definition how it can be related, that is a surface integral of d dot ds is equal to q. So which is nothing but what? Flux. So this is in terms of electric field, so I am denoting the symbol as phi. Okay, so for magnetic field, let me go with the Gauss law for magnetic field. Previously, we have seen for the electric field. Okay, so the Gauss law for magnetic field. is nothing but the surface integral of B dot ds is equal to 0. Okay, is equal to 0. So applying the divergence theorem. Okay, applying the divergence theorem. So that what is the divergence theorem? Why we are applying the divergence theorem? The divergence is nothing but suppose I am telling this is one conducting element. When I am passing the potential, okay, when I am passing the potential to this conducting element, what happen? The electron will start move. Okay, once the electron will start move, the magnetic flux lines will be generated over here, and it induces EMF on this conducting element due to the flux lines. Okay, so this is nothing but your reality. Okay, it is diverging. It is diverging from this point. So I am applying divergence to the above expression. Apply. Okay, apply divergence theorem to the above step. So if I apply to the above step, what happened? Instead of the integration, the function becomes del dot b equal to 0. So it look like wow, solenoidal expression. So where b is any function, but here b, what is b? It is a magnetic flux density. Okay, it is magnetic flux density. Okay, so whenever del dot any function is equal to 0, I can tell it is a solenoidal. Okay, it is solenoidal, and also in this case I says the statement that total magnetic flux passing through any closed surface area is equal to 0. So here what is the closed surface area? This one only, this conducting element, which is applied with some potential. Okay, this is one closed area. In this closed area, what is the magnetic flux is generated? So why we term density? Okay, why we term as a density? Suppose I am showing this one. What is this? This is one pen. If I am showing at one angle, you can see one point only. You don't know what is this geometry. If I am showing fully with like this only, you can able to see what is this specific geometry or object. Correct. If I show at any one side like this, okay, you can see only the point. Okay, so like that only if we do the analysis with the point form, okay, so we not put any differentiation or integration. Okay, if we deal with some volume or density parameter, then it will be deals with the that is integrations. Okay, let me go with the another concept called moving force on a moving charge. Sorry, magnetic force on the moving charge. Magnetic force on a moving charge. What is this, sir? Okay, so magnetic force on a moving charge. Suppose I am taking one conductor. This is one conducting element, a point AB. When I am applying the potential, what happened? The electron will start spinning. So actually, we are talking about the electron. Okay, it will be fully charged. Okay, it will be fully charged, and the electron will move with the velocity v, and it has the magnetic field also. Okay, it has the magnetic field b. Then 1 minute. A bit under tell. Yeah. Suppose I am telling the charge is induces the some field component. Okay, the charge Q induces the field E on the axis. Then what about the magnetic field? It is perpendicular over it. Okay, it is perpendicular over it. I am not drawing perpendicular. Okay, perfectly since due to some space constraint I have drawn like this. It is somewhat perpendicular. Some magnetic field has been obtained. So then how the force experienced for this given conductor has been written in mathematically. Please see, in this single conductor, once you apply the potential, the electron will be starts flow with a velocity v. Okay, with the velocity v. Okay, so after that, it will induces some charges on this conducting element. A field will be produced on the axis. So electric field. The electric field also induces magnetic field which is perpendicular over it. Then what is the force experienced on this conductor? So the direction of the force is perpendicular to V and B. So I can write this equation like this: F is equal to Q into V cross B. V cross B, where V is nothing but the velocity. So then you know that vector identity formula A cross B can be written as AB sin theta. AB sin theta. So this equation can be written as VB sin theta. This is your first equation. But in general, in Coulomb's law we have studied, in general the force experienced for the single point charge is nothing but F is equal to Q into E. Okay, this is for a single point. So PT is nothing but a point. Okay, so a single point charge, the force experienced in the conductor. Okay, the conductor. So this is the general formula we know. Then what is the total charge obtained? Okay, what is the total charge obtained? So then we have to sum up first and second equation. So you will get the total force like this. Okay, adding first and second, so the total force becomes Q into E plus Q into V cross B. This is nothing but, what is this equation? If any, since you have studied in physics, you can tell this equation is called as what? What is this expression? You have come across with this expression. So this expression is called as Lorentz force. Maybe you have studied in other form, I think that also I will tell. Okay, so here you have one charge, electric field, V is a velocity, and B is the magnetic flux density. Okay, it also, okay, it also defined like this. Okay, it also defined in other form. This is one form in terms of charge, in terms of electric field, in terms of magnetic field. Okay, so the same Lorentz force may be defined like this. Maybe this equation you may studied. So suppose you have the conducting element. Okay, conducting element pass a current. Okay, conducting element pass the current. The conducting element of length L. Consider the length L. Okay, so once the current flowing into the conductor, what happened? The field will be induced on it, and the magnetic field will be there somewhere. Since we are dealing with the magnetic field, I am talking about magnetic field alone, but electric field also along with the axis. Okay, so if I tell routinely all concept electric field, don't get confused. Okay, so since we in this module we mainly focus on the magnetic field. So then what is the force induced on it? So the force can be given like this: the force is equal to I cross B into A. So what is IB? IB is nothing but I into B sin theta. So I can write BIL sin theta. So maybe this expression you may studied in your 12th standard physics or in physics subject also. So this equation is also called as Lorentz force equation. So based on your requirement, okay, based on your requirement in your given geometry or given constraint, you have to take this formula. Okay, let me go with the one postulate and we will stop with the today's class. I hope everyone know about the Bayet-Savart law. Bayet-Savart law. So, what is meant by Bayet-Savart law? Can anyone tell quickly? I want quick response if you know. Otherwise, I will move forward. So, if you know the static electric field concept, that is Coulomb's law, then definitely Bayet-Savart law concept can explain.
So it's that current is directly proportional to length.
Yes, current element is directly proportional to the length. Like that, you're telling?
Yes, sir. In a magnetic field.
Okay, okay. Yes. Thank you. Thanks for your response, Sasha. It is correct only. Okay. So actually, we are dealing with the current element. Okay, that is magnetic field at this differential current element. Actually, consider this is the I will differentiate in different color. Okay, so maybe so this is nothing but your current element. Consider this is current element is nothing but a wire, normal wire of a length L. Okay, of a length L. But I am considering DL is the small part of the length. At this point, okay, what is my magnetic field obtained at the point P? Up to the point P, I can obtain my magnetic field. So in a classroom, if I shout, okay, up to that classroom alone, you can able to hear my voice. But I cannot. But my voices cannot be here apart from that. Okay. So then, if I want my voice to extend, I want the mic, okay, to amplify it, so that it may reach to some wider. Similarly, here the magnetic field obtained up to certain distance of r. Okay, so then what is the postulate of given through this Bayet-Savart law? The magnetic flux density produced by the current element at any point in a magnetic field is proportional to the current element. So what is the current element here? IDL. IDL is nothing but the current element and inversely proportional to the square of distance between them, as you studied in the previous concept. So that I will write the statement. So it will be the magnetic flux density. So magnetic flux density means you should remember what is the denotation. It is nothing but capital B. Okay, produced by a current element. Okay, produced by the current element at any point. Okay, at any point in a magnetic field. Magnetic field means which one I can define its field. Magnetic field is proportional proportional to the current element. Current element means ideal, this factor. Okay, to the current element and and inversely proportional to square of distance between them. Okay, so this is the statement given for the Bayet-Savart law. So then how it can be related mathematically? Okay, so mathematically, so the magnetic flux density, how can we define? It is for the single point only we are talking. Please see, for this single point, please see, for this point, dot point only we are looking on dl. Okay, so then ideal is nothing but the current element. So the field produced also we have to represent like dB only. So the dB is directly proportional. Okay, dB is directly proportional to ideal and inversely proportional to square of distance between them. So if you removing the proportionality symbol, okay, so then in magnetic field we have to introduce a constant called mu. So there we have introduced a constant 4 pi epsilon. Okay, 4 pi epsilon, but here 4 pi will come in denominator. Okay, so there we have introduced 4 pi epsilon. Here mu divided by 4 pi. 4 pi comes in denominator. Okay, so ideal into r square. So this is one single point. So you can mention one unit vector also. So a vector. A vector is the unit vector. Okay, so where mu is nothing but what here? So mu is nothing but mu naught into mu r. So that is permeability of the medium. Permeability of medium. So where IDL is nothing but a current element. Where R is nothing but a distance between the point P and the current element. Okay, distance between the point P and current element. Where A vector is nothing but the unit vector. Okay, so since we're dealing with the magnetic property, so each vector comes in perpendicular to your E field. Okay, so then how come you can write this above expression in magnitude? Its magnitude. Actually, one thing I forgot to tell, it is ideal means you should not write ideal like this. It's like I cross dl. I have simply make it as ideal. So you have to write like I cross dl. So it is in a vector. Okay, it's in vector, so you have to mention it as I cross dl. So I is one vector and dl is another vector. So as per the vector identity, a cross b can be written like ab sine theta. So then its magnitude can be written like this: db is equal to mu ideal sine theta whole divided by 4 pi r square. Okay, 4 pi r square. So now we already relate one expression like magnetic flux density. What is magnetic flux density? B is equal to mu into h. So you know the relation. So this also in electric field how we define D is equal to epsilon into capital E. So just to see the resemblance, the same property only. But the thing alone, the representation and the terminologies is different. Okay. So then above equation, how we can relate this expression? Okay. So instead of dB, I am going to write. So how can I write dB means uh, B is nothing but mu into h. Mu is a constant h, which is equal to above step is mu idl sine theta whole divided by 4 pi r square. Now you simplify, mu get cancelled. Okay, mu get cancelled. So where dH is equal to IDL sine theta divided by 4 pi r square. So this is your magnetic field. Okay, this is your magnetic field, but see, it is denoted as dH. So if it is dH, it is obtained at this point only. But I want for the full length, then what I have to do? Whether I have to do the differentiation or integration. Can anyone tell? If I want the